Internal combustion engine design, testing, and performance. Sample problem number 4. Single cylinder and 4-stroke cycle internal combustion engine when tested. So we have a single cylinder 4-stroke internal combustion engine when tested. The following observations are available. So the area of the indicator diagram is 3 centimeters squared. The length of the indicator diagram is 4 cm. The spring constant is 10 bar per cm. The speed of the engine is 400 rpm. The brake drum diameter is 120 cm. Dead weight 380 newton. Spring balance reading is 50 newton. Fuel consumption is 2.8 kg per hour. Calorific value is 42,000 kilojoules per kilogram. Then we have the cylinder diameter 16 cm, piston stroke 20 cm. So we need to find first the friction power. So friction power, as defined, is just the difference between the indicated power and the brake power. So these are the power that are being wasted as your power is transmitted from the combustion engine to the output shaft. So we need to compute for IP first and then the BP, because IP and BP are not given. So for IP, so we are already familiar with our formula in finding IP. You can recall in slide number 31. IP is simply PMI times LAN times K divided by 60. So we need to divide N with 2 if we have 4-stroke engine. PMI is the mean effective pressure based on indicated power. So going back, so first, for us to use this formula, we need to have PMI. So we already have the length, that is the stroke 20 cm. The area can be solved using the diameter. K is the number of cylinder, which is a single cylinder. N is, since this is 4-stroke, we divide our given speed, which is 400 rpm, by 2. So we are left with PMI. So for PMI, so when the area of the indicator card, length of the indicator card, and the spring constant is given, we can still solve for the PMI. So using this given, so PMI is just, so you can constant divided by the length of the indicator card, or the length of the indicator diagram. So this is the diagram that will show us the PMI. So if that is given, we can solve for the PMI. That is why for this problem, substituting those given in this formula, we can solve for PMI as 7.5 bar. In kPa, that is 700 kPa. So we need to convert it to kPa so that when we substitute it in our IP, the result is kilowatts. So IP is PMI times the length times the area, pi over 4 d squared, times n over 2 times a single cylinder, which is 1, divided by 60. So our result is 10.053 kilowatts. So for the brake power, we instead, because we don't have the value for the torque, so if you are going to look at our given, we don't have torque, so that's why we will use another equation for solving the brake power. So in slide number 62, the brake power can also be solved using this. Brake power is pi dn W minus S. W is the dead weight. This is an instrument in measuring brake power. So W here represents the dead weight. S is the spring balance, measured value in the spring balance. N is the RPM. D is the diameter, the rope brake diameter, which is also. So we can solve for BP by substituting all those values in the formula. So pi, our D here represents the rope brake, the diameter. which is also given. The brake drum diameter, so which is 1.2 meter. N is the number of revolutions per minute. We need to convert it to seconds. So we do not divide it by 2. So we will only use that for IP. Then W, which is the weight, the dead weight, which is given 300 Newton, minus the spring balance reading, which is 50 Newton. So we need to convert Newton to kilonewton so that our result is in kilowatts. So that's why our BP is 8.293 kilowatts. So now that we have BP and IP, we can solve for the friction power, which is IP minus BP. So we have friction is 1.76. The next one is we need to solve for the mechanical efficiency. So for the mechanical efficiency is BP over IP. So from our values in given for solved in A, so we have mechanical efficiency as 82.49%. The next one is the BSFC. So the same solutions as sample problem number 2. So mass of the fuel divided by BP. So for this problem, we can see that we can also express BSFC in terms of kilogram per kilowatt hour. And then brake thermal efficiency. So brake thermal efficiency, we already have BP, the mass of the fuel times the heating value. So that's why we have 25.39%.